The elementary building blocks of classical computers on a formal level are bits. The same principle applies to quantum computers. Those building blocks are called quantum bits or qubits in short. It's their special inherent physical property which gives quantum computers their supremacy over classical ones. Let's dive into.
First of all, recall the classical bit, the smallest unit of information represented by two different states, which are labeled 0 and 1. In electronic devices, like in flash memory cells, those values are encoded by voltages where the state 0 is referred to low and state 1 to high voltages. For a classical bit, the information is stored collectively by particles, in our example of flash memory cell by several magnitudes of order of electrons, typically 10 to the power of 5. The same concept of a bit can be mapped onto the quantum world. A prototype example of a qubit is an ion in a linear ion trap. The trap consists of several magnetic fields which hold single ions within this longitudinal X. The label 0 of the qubit then is associated with the low energy state and label 1 with an excited state of the ion. Beware of the difference between classical bit and a qubit. In a qubit, the information is stored in one single particle instead of a large amount of particles, as in the case of the classical bit. Let's formalize the idea of a qubit a little bit more. In quantum mechanics, the states are described by elements of a complex vector space and denoted by a well-established bracket notation. In this notation, the two states of a qubit are denoted by cat0 and cat1. Now here is another difference to the classical bit. Quantum mechanical systems can be in states which are beyond our real-world understanding, in so-called superpositions. This means a qubit cannot only be either in state cat0 or cat1 exclusively, but also in states in between. The physicist Erwin Schrödinger illustrated this phenomenon in his Gedankenexperiment called Schrödinger's cat. In this experiment, a cat in a closed box together with a poisoned apparatus is neither dead or alive as long as someone doesn't open up the box and look for. The superposition property is a direct consequence of the linearity of the underlying complex vector space, since any linear combination is physically valid. In our example of a superposition, cat0 plus cat1 prefactored by 1 over square root of 2, the qubit is exactly between the two states. Again, the qubit state, psi, is given by the linear combination of cat0 and cat1 with complex coefficients C1 and C2. And because of the probabilistic nature of quantum physics, states vectors are normalized, meaning that the sum of C1 square and C2 square equals to 1. Since C1 and C2 are complex, and we are free in the choice of the parameters used, we can rewrite the state psi by using angles phi and theta, which gives us a very powerful geometric interpretation of the qubit. In this interpretation, a qubit state can be seen as a point on the unit sphere where the antipodes along the z-axis are identical to the states cat1 and 0. In the context of qubits, this sphere is called the Bloch sphere. With the interpretation of the Bloch sphere, we get a glimpse on how information on quantum computers is processed, namely as rotations of points on the Bloch sphere. For this, remember your linear algebra class, where rotations of vectors are facilitated by the multiplication with rotational matrices U.
And here's a question for you. Can you find the superposition state discussed in this lecture on the Bloch sphere?